So we did compactness, and completeness is sort of very essential, and it's completeness is in a way, what to say? I mean, it's obviously weaker than compactness. Okay, it's weaker than compactness. So if a space is compact, it is definitely complete, but it's not vice versa. Okay? So completeness in metric spaces. Metric spaces. So again, a general reference for this would be that you should read is metric space. There will be a chapter on completeness and metric spaces by the same authors. Okay, Satish Shirali. Okay. And yeah, this there'll be a chapter on completeness that you should read, and also Moncrief's topology. Okay, but you don't have to read the topology part for this because completeness is a metric property to begin with. So you can see this chapter 7 in Moncrief's topology. So topology by Moncrief. Chapter 7. So there is a chapter on complete metric spaces and function spaces. So you should try to read as much as you can from these two. It's important. Yeah. All right. So obviously we will be fixing a metric space x comma d, okay, and a complete metric space. So what is the definition of completeness? Anyone?
Every Cauchy sequence converges.
Every Cauchy sequence converges, right? So Cauchy sequence we know, and then every Cauchy sequence converges. So that's the definition of a complete metric space. Right. So I mean, as usual, can you give me any examples? Let's think. Examples. Yes, any examples of complete metric spaces? So every Cauchy sequence converges. So if you have a sequence which is Cauchy, which means if you start with a Cauchy sequence, which means, so I'm just reviewing the definition of Cauchy sequence. Given any epsilon, there exists an n naught, or maybe n epsilon, such that xi minus xj, well, so this is not correct. D, because it's not necessarily reals, right? So d of xi comma xj is less than epsilon for all I and j bigger than n epsilon, right? This is just the definition. Then this implies that xi converges in such spaces. So what is an example of such a space?
R.
Exactly, right. So R is a complete metric space, and that's the fundamental one. To prove that anything else is complete, you either use that R is complete, or you use some theorem which uses that R is complete. It's somewhat like that, right? Yeah. So that's the point. So R is complete. So maybe we should is R is a complete metric space. I mean, so the question is, how do you prove this? How do we prove that R is a complete metric space? Yeah. So, well, I think it depends on the definition. It depends on how you define R, right? So here is one of the definitions, right? That, or maybe axioms. So one of the axioms for R, maybe axiom, R has LUB property, right? So what does this mean? This means that every bounded set, every set that is bounded above, okay? So R is a set and it has an addition, so on, so on, it's a field, but it has the LUB property. Okay? Every set that is bounded above has a supremum. I just call it axiom because this is the only thing that we will be needing to call axiom in this discussion. So this axiom, okay. Now you should show this, that this axiom implies that R is complete. Okay. So any ideas and intuitions why this will be true? So what this is saying is, see, if you want to show that R is complete now, if you assume this very big thing, then it's almost very simple, because this is almost in general we just say that this is the same thing. This is called this is also called completeness actually. So how would you prove R is complete? Well, you take a sequence, you take a Cauchy sequence. Okay? So take a Cauchy sequence, right? B Cauchy. I mean, this implies that xi is bounded. Yeah. What can you do from here? I want to show that the Cauchy sequence converges. Yeah. So one of the things that I can say is that this implies that xi has a monotonic subsequence, right? That's again something that we know. Any sequence has a monotonic subsequence. Xi has a monotone subsequence, right? And then you take that subsequence, call it xij, right? Yeah. Take the supremum of this. This is monotonic. I mean, it's monotonically increasing. I mean, even if it's monotonically, okay. Because it's Cauchy, so it's bounded both above and below, right? Yeah. So it is, so either you take the supremum or you take the infimum, right? And you can show that, I mean, if set is bounded below, then it will have infimum. If you assume this property, supremum existence, then you will also get the infimum existence for free. That also you should prove, right? So this implies the infimum property. Okay? That's sort of almost obvious because there is a symmetry, but you should prove it. Okay? And then this supremum or infimum which you take, I mean, depending on whether it's increasing or decreasing, that will be your limit. That will be your limit of that subsequence. So this subsequence will converge, right? So we have a convergent subsequence. Yeah. So we have a convergent subsequence. And then you know that if a Cauchy sequence has a convergent subsequence, then it will itself converge. That's another aspect of Cauchy sequences, which again you know, or then you should check it out, right? And that's not very hard to believe, right? If a Cauchy sequence has a one subsequence which is converging, right, then the whole thing will converge, of course. That's what. Okay. So this LUV property, and so all these are completely formal steps, nothing, something which is comes before this. So this is you should work this out in detail. The point is this is important, and what you should understand from here is that when you say R is complete, it really depends on how you define R. So if you define R as a field with ordered field, an ordered field, and then with the LUV property containing the rational numbers, or you don't really need it to contain rational numbers. So any ordered field with the LUV property will be complete. So LUV property is completeness. Okay. So that's the same thing as completeness that you should understand. It actually had nothing to do with R. You can take any ordered set which is an ordered field with the LUV property. Ordered field, and you'll also need a notion of distance in the field. So normed ordered field. So this is a simple thing. Fill in the details. But see, you should fill in the details, because filling in the details is how you will realize certain things on your own, which you do not realize when I say, right? That's very important. Yeah, so there are some other aspects which maybe I'll write here, which we would want to talk about. Cardinality of complete spaces. But maybe a little later. Yeah. So yeah, I mean, if you use this definition, then you are done. But what now if you don't use this definition? Then how do you define R? See, then how do you define R? That then comes to the definition. Then only you can prove something, right? If you defined it, then only you can prove it, prove something about it. So then it comes down to a definition of R, which is a slightly different discussion than completeness in metric spaces. Okay. So this will be another idea which I will be putting, and you should then see. Okay. So maybe not defining, this is about constructing the real numbers. Constructing R from Q. Okay. So can you give an example of a Cauchy sequence in Q which does not converge? A Cauchy sequence. So now we are completely in Q and we are asking this question. A Cauchy sequence which does not converge. Yeah, think about it. So just the simplest examples will work. Yeah.
We can take the sequence 1 plus 1 by n or
Hmm.
power n.
Power n.
Is this?
Okay.
Yes.
Oh, okay. Right. Yes. Because this, because you know that this sequence is Cauchy, you should check that it is Cauchy because it converges in R, right? So if something converges to
Yes.
something outside, it means it will be Cauchy inside also, because Cauchy is an intrinsic property which doesn't refer to the limit. So, but it converges to E, right? So it cannot converge to anything else, and so it cannot converge to anything rational. So it comes down to proving, and this you can again take as a nice. This is, I think, a nice thing to check. Is E is not rational? Not difficult to prove, but you should prove it, or you should try to check out a proof, right? If you have done it, it's good. Otherwise, just check it out. Okay. And if you have done it, then you should check out E is transcendental. If you find the first one easy, and tell me next. Second one is a bit hard, but and transcendental, if you know the definition, check it out. Okay. E is not rational is a nice exercise. It's easy. On the other hand, proving that pi is not rational, I suppose, is more difficult. Okay. Easy in the sense that it's you can understand it easily. Whether you can do it or not, that you have to see. I mean, if you start with the correct definition, first you have to think, okay, I want to prove this, and what definition should I start with? That's one of the things. And then you try to show that if you start with that definition, that convenient definition, then you can easily prove it. And then you go back and try to show that that definition is equivalent to this definition, which maybe I suppose, yeah, you would want to. Right? So proving that E is not rational is sort of equivalent to this exercise. Okay, I mean that's what you do. That's how it is, I suppose. Okay, so that you should do. But yeah, so this is. I mean, there are examples like this. Right? So it's not a big deal. Okay, so of course, so you sort of understand what this not being complete means, right? Not being complete. It kind of is giving you this thing. Okay, something is not complete. You can always put it inside something bigger, which is complete. Like you can take the Cauchy sequences and you can uh, kind of artificially add their limits, right, and get a bigger space. But of course, there are still a lot of things to be checked. Yeah. Right. So how do you construct R from Q? So there is a construction which I know so very very well. So I'll probably not try to say that one, but I'll try to say a construction which I don't remember very well, and that is based on Dedekind cuts. And this is Rudin's first book, first chapter, Baby Rudin first chapter. Yeah. It may be there in other places, obviously, but I remember it that it is there. It is there in that book. This might not be there in those two other books because they don't deal with this kind of topics. These are sort of set theoretic topics, which I mean, yeah, I don't know, it might be there. Dedekind cuts. Yeah, yeah. So what is that? What is it? I mean, I'm not giving you a full intuition because you will get it when you see the construction and when you listen and you see and try and you will get the intuition. But what is a Dedekind cut? That's the thing. So that I should define clearly, otherwise it will be confusing. Definition. And the problem is I do not know the definition very well. So I don't know what notation to use. So let's say C. C is a Dedekind cut. So maybe what is a Dedekind cut? A Dedekind cut is of course going to be a subset of Q. That I can understand. From what I want to do, I understand it should be a subset of Q. And you see, we want to take the subsets of Q, which are sort of the sequences which we want to converge, but they don't converge in Q, right? So these subsets themselves, we will now call, somehow we will give them the status of a number. Okay, that's the idea, that these sets which we want, these sets which are the sequences which we want to converge, or rather which don't have their supremums, or which are Cauchy sequences but don't converge, all these are sort of similar, right? So these sets, we want to give them the status of numbers, right? So for basically then you're done, because then this Cauchy sequence or this set now becomes a number, and that number would be the limit of this Cauchy sequence. But then when you give a set the status of a number, then you have to see that this new number which you have, right, mixes well with the original other numbers which you already had in Q. So how do you do that? Well, there is something, but I will write with a definition, right? So yeah, so it's like there is the E and there is a sequence converging to it, and that sequence converging to it we want to sort of call a cut. But uh, but maybe we will take everything that is less than that. So maybe that will put in the definition C in Q, and maybe yeah is called a cut. Okay, so C in Q is called, right, so such that Y in Q, okay, implies X less than Y. No, sorry, yeah. So I will fumble here a little bit. So it means we should see Y in Q, and this X less than Y implies X is in Y in C. It's already in Q. I mean, if I say this, it's already in Q. So I'll just say this. So this is one of the properties, and this property is, as you can understand, it's sort of like downward closed. These are nice sets. These are basically the intervals, right? From infinity to, but yeah, open intervals sort of, you could say. But these are open intervals in Q, so you have to be careful. So this is one of the characteristics, and I believe that it should have a few more characteristics. Let me see. Okay. So this is Rudin. This is, yeah, baby Rudin. Yeah. Okay, got it. So this definition is mostly the definition that you will need, but I will make a few changes to the notation, okay, because it's sort of very wise here. Because we want to give these sets the status of a number, we will not really denote them by in the usual set notation. We will denote them by small notation, okay, so that, yeah, all right. And so now you understand this property, right? If the set and this happens, yeah, and X is less than Y, then it implies that X is also in alpha, right? Right, and of course, I mean, this X has to be in Q because everything is happening in Q. We don't have real numbers at the moment. They don't exist at the moment, right? So this is property number one. And there are a few more properties, but they are mostly to avoid certain issues. This is to get the things that we want, and then the other two are sort of to avoid certain issues. And the thing is that alpha is not equal to all of, because that the limit of all the rational, the particular collection of all rational numbers, the supremum of that is not something that we would want to have. Yeah. Yeah, and this kind of forces it to be bounded. Do you see? This forces alpha to be a bounded set, bounded above, right? It forces it to be bounded above. You can see that. And then the third property, this is also kind of very important, yeah, because and what if it, yeah, well, let me write the property, yeah, that y is in alpha, okay, implies there exists r bigger than y, okay, such that r is in alpha. Okay? So it says that it's a strictly open interval. It's kind of it says that it's a open interval. Okay? So it doesn't have a maximum. Yeah. If there is a y, then there's always something bigger. Yeah. So that you may say that it doesn't have its limit. Okay, it doesn't have its limit. Because see, if it had its limit, right? I mean, if you don't put this condition, then you will get some set which is sort of converging to half. Okay, let's say, and then you will take this set. You'll take this set in as a cut, as an example of a cut, right? So a cut is this, yeah, a cut. So a Dedekind cut is a subset of alpha. A Dedekind cut is a subset of is a set alpha, which is subset of Q. Yeah. But you see, if you don't give the third condition, then there is always a problem, right? Because you will take this set and you will always take this set, right? But then both of them you would want to, so these sets are basically your rational number half. They will correspond to your rational number half, right? Agree? This is what you would, this is what will correspond to your rational number half. This is opposite to what I said. We wanted to lift certain sets to the status of a number, but then we are thought of what we are doing is we are bringing down the numbers to the status of a set. Well, bringing down, don't take it in that way, but you understand, right? Yeah. And so this is the point, okay? That these two we don't want to, but yeah, but then these two, if they give the same number, then I mean, two different cuts will give you same number. We don't want that, right? So, and we don't, so that's why this is a choice. And that's why the third condition. Just a, it's just a non-trivial open interval which is downward closed. And everything is in Q. Right. So basically, I mean, these are our cuts. Okay. These are our cuts. So now what would you do with this? Now you see, what we want to do is, first of all, maybe this D is a collection of all Dedekind cuts. Okay. Firstly, you can see that its rational numbers are sitting inside the D. Every element of D is a set, right? Right. So alpha is a cut. Okay. And the collection of all cuts is D. So that we'll write here, maybe is better. So collection of all cuts is D. Now we come to the actual things. Firstly, you can see that your Q sits inside D. How? I mean, sits inside meaning is sort of the wrong word, but you can take a function. You could take a function from the rationals to D. How? I mean, you just take a rational number P by Q and you just send it to this interval. Obviously, I mean this interval meaning rationals, of course. A rational interval means every point rational, right? This is of course in D. I will not write that because that's given here. Okay, so it's an injective function, right? So you put this in inside D and it's an injective function. Now what to do? What do we do now? Well, now you want to say that this D is your collection of real numbers, right? D will be somehow the real numbers, the elements of D. Every cut will be a real number. You understand, that's the intuition, right? Yeah, the cut, like this cut will be the number E, right? So you have to give the structure of a field on this cut. So how do you do that? First, you put the structure of an order, right? So D with respect to the inclusion order, I mean, the order given by inclusion, right? Which means that, I mean, you say that one cut is less than another cut, which if and only if this happens. So we use the basic order on sets, the most natural order on sets. Okay. Correct. So you put D with this order, which is the natural order, and then you can check that it's an ordered set, is an ordered set. I mean, that you should. Do you need to check that? Because it's like set inclusion is always an order. Because it may be partial order, but here it's not a partial order. That's the key. Is an ordered set. You have to check all the transitivity and so on, right? Yeah. Transitivity, antisymmetry, and so on is an ordered set. So you check that. Maybe I'll erase this. So, I mean, as the book does, I will follow the book. I will say that this is R, because that's a better notation. I'll start calling this R. So we don't have to think we have to think one less thing. Yeah. The collection of all Dedekind cuts, I will now call R. Okay. And now the key thing here, which is because you see now this R is an ordered set. Okay, R is an ordered set. So you can talk about supremum property for R, for this ordered set. Any ordered set you can talk about supremum property. Agree? Right? So you just prove, right? Then you prove that R has supremum property, and it's very easy actually. Just take unions and whatnot. Right? Yeah, you just see. Okay, you take a collection of you take a subset in R, then you have this, basically it's a collection of intervals. You take the union of the intervals, right? And that will also be in R, and that will be the supremum. So R has supremum property, or maybe it's LUB property in our notation, but somehow, oh yeah, here also is written LUB, but somehow, right? And now we are mostly done, right? Right? We are mostly done, because you have basically pushed a Q into something which has the LUB property. But then you have to define a field structure on R. You have to define addition on R and so on, right? How do you do that? I mean, again, this is just going to be obvious, right? So if you take alpha and you take beta, how would you define this summation? Well, just the union, because what else can you do? Yeah. I mean, no. I mean, yeah. So if you this obviously you want to take the set sum. It's just a set sum, right? Yeah. So union will obviously not give you, right? Because you can understand if it's half and then 1/3, and the union will just be 1/3. So that's not the answer, right? You have to take set sum. Okay. So this is just set sum, right? So this is just set sum x plus y, where x is in alpha and y is in. Right. So just take this set sum. So it's a very fantastic thing, because I mean, one of the things you're defining without using the LUB property, you just prove without using this addition structure, but then you put an addition structure. Okay. So here you have to think of, if you read a few things, like it becomes a field. It becomes a field, and then you have to show, and all these are easy things that show that those two things above, order, we have order, order and the field structure. This give you an ordered field in this case, meaning that if x is less than y, then x plus y is less than, or alpha, beta, whatnot, right? You understand that thing you have to check. And yeah, then it's mostly done. Just a few more things you have to do, associativity of addition and so on, but yeah. Okay. So anyways, let's come back, and then we will sort of see that one side of the discussion which is left after 10 minutes. And then we will apply this to more interesting things to prove other spaces are complete. That's more important than, yeah. I mean, that's the other aspect. So let's meet in 10 minutes. You think about this. This is